Welcome to Saxon Math, Lesson 96, Estimating Angle Measures. And we'll also be doing the distributive property with algebraic terms. Positive, negative. Looking at this, we can see negative 27 minus negative 50. So two negatives do make a positive. So we can really just think of this as positive 50 minus 27. Gets us 23. Order of operation, exponents. 5 times 2 is 10. And then looking at our exponents, we're multiplying these like exponents, so we just add them together. Which would get us 10 to the 12th power. But hey, we've already got 10 here, so really we can pass that on over to the other to get us 1 times 10 to the power of 13, which really is just 10 to the power of 13. Algebra. Minus, we can start just by minusing 80 from each side, which gets us 80 equals 4y. So divide each side by 4, gets us 20 equals y, which is, in fact, exactly the same as y equals 20. Measurement. Convert 15 degrees Celsius to degrees Fahrenheit. We can start by multiplying by 1 8/10. Get us, remember this, boingy. So we take this decimal, boingy. 27 plus 32. Get my chicken scratchings out of the way there. Gets us 59 degrees Fahrenheit. Calculation, 1 times 9 is 9, and 2/3 of 9 is 6, getting us 15. Percent, 25% more than 80. Well, 25% is just 1/4, and 1/4 of 80 is 20. 20 plus 80 is $100. Geometry. A regular solid measures 5 inches by 3 inches by 2 inches depth. So that's essentially 5 times 3 times 2. That's 15 times 2 is 30 cubic inches. Estimate 15% of $49. Well, we can just say $50 since we're estimating. And not sure of a shortcut to get this into a purely mentally math form for us. Gets a 750. However, we're really looking at this like that. So we can go boingy, 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 boingy. Gets us $7.50. All right, so starting out, estimating angle measures. And I like that they're using the clock for this because I've always liked the angles inside the clock angle. But one thing we can see just looking at the clock is that if we are at the 3 o'clock time point, we have an exactly 90-degree angle. So judging that by that, we could say, well, if that's 90, then this must be 60 degrees, and this must be 30 degrees. And if that is true, then we can look at these smaller increments and say that, well, then this would be 5. Oh, I should say this would be 6. Excuse me. 6, 12, 18, 24, 30. So every minute on the clock represents a 6-degree angle shift. Every number on the clock represents a 30-degree shift. And we could just keep on using that all the way around. So at 120, this could be 150, and so forth. In fact, that works so well that it sort of renders the first example almost a little bit moot, because they give us a bunch of gymnastics to go through to estimate, but I don't think we really need any of it, because looking at this, so just let's look at the example though. Estimate the measure of BOC in the figure below. Then it says use a protractor to find the measure of BOC, which, no, you don't have to put a protractor up to the screen or on your book, or if you don't have a protractor, do not worry about it, because I don't think we even really need it, especially looking at our clock. How many degrees did your estimate differ from the actual measurement? But let's look at this. I don't know if I could get these right on the line, but they don't look like they want to stay. But looking at this, this really, really looks like it's exactly halfway between the 2 and the 3. At least it does to me. And so looking at that, we could say, well, if this is 60 degrees and this is 90 degrees, well, exactly halfway through there would be plus 15. getting us 75 degrees. So they went through a bunch of things to explain why their estimate was 72 degrees, but I don't really see that. I think it's very obviously 75 degrees. But using their protractor, they measured it at, indeed, exactly 75 degrees. But I think that we can estimate it just fine using our clock. And then they jumped over to the distributive property for their next examples. I'm not sure why these two things are in the same lesson. I think that they should be tied in some way, but I don't see it. Maybe you can earn yourself a virtual pom-pom by telling me, how are these two examples related to each other in the world of mathematics? But I guess switching gears over to the distributive property, we can shift things around, and the distributive property is frequently used in algebra to simplify expressions and solve problems. So looking at our examples here, we can say 2 times x minus 3. Well, we can just take our times 2 and apply it to each part. So looking at A, we could say 2x minus 6. 2 times x is 2x, and 2 times negative 6, or 2 times negative 3 is negative 6. Okay, looking at B. Yeah, I totally meant to do that. Negative 2 times x, negative 2 times positive 3 is negative 6. So we get negative 2x minus 6. Okay, looking at C. So now I've got negative 2 times x, and then negative 2 times negative 3 gets us positive 6. And then finally, D. Okay, well, pretty much the same thing, except now we're using a variable. So x times x is x squared. X times negative 3 is negative 3 times x. Pretty basic, right? So applying this to a larger problem still really isn't too tricky at all. X squared plus 2x plus 3 times x minus 2. So we'll just do this part first as similar to our other problems. So we can just bring that down for 3x minus 6 So now looking at our x squared plus 2x plus 3x minus 6. But now we can combine our like terms. So positive 2x plus 3x will get us 5x. And there's nothing really much we can do with the rest of these. getting us to our solution of x squared plus 5x minus 6. Okay, so now please be sure to do all the practice set problems. It appears to be quite robust today. And we will check the practice set in the afternoon. All right, well, thank you for joining me, and I will see you at our 10:30 meeting.